Hi, this is Mr. Maryland. In this video we're going to talk about how to draw qualitative force diagrams. So I have two examples for you. The first one we're going to look at is number 3 on the set of practice problems, and we're interested in a magnet on a fridge. So we're going to draw a system boundary around that magnet. Okay, so that system only includes the magnet, nothing else. Of course, you can have systems which have more than one object. This one just has the magnet. So now that we've sketched the system in the surroundings and we've enclosed the system within a system boundary, we want to take that system, the magnet, and shrink it to a point. Okay, and we're going to begin to draw a force diagram. Alright, so the first thing we should do is once we have this point, we should sketch a set of parallel and perpendicular axes. And it's pretty obvious now in the examples you've seen so far that one axis is going to be like this and the other axis is going to be like that. But we should jump ahead and think about the rules a little bit. It says we want one axis to be in the direction of motion, if there is motion. So that is not a complete rule right now, but it's good enough for the time being. So if the problem says that this magnet is sliding down the side of the refrigerator, so if the motion is going to be in that direction, we want one of our axes to be along the refrigerator there, and then the other axis has to be perpendicular to that. Okay, now we can start thinking about the forces acting on this. So the first thing you should think of is the gravitational force that's going to be present in every single problem. So we're going to go ahead and draw a vector for that. So that's my gravitational force vector, and I'll go ahead and label it appropriately. It's a force. Its type is gravitational. The feeler of this force is the magnet, and the dealer of this force is the Earth. Okay, so we have type, feeler, dealer. There's a few other forces here. Well, what's going to oppose this downwards gravitational force? Because at the end of the day, we have to have the net force add up to equal 0 if we're going to have this thing moving at a constant velocity. Well, one force that I can think of that's going to oppose this downward sliding is a frictional force. So that's always going to be, every frictional force will be parallel to the surface. We have the surface of our fridge right here. So I'm going to draw a vector points in the opposite direction. Because this is a motional frictional force, this will be kinetic friction. It acts on the magnet, and the source of this frictional force is the fridge, the surface itself. The source of every frictional force is a surface. So what's some other things? Well, you're in contact with the surface here. So every time you're in contact with the surface, such as the side of the fridge, we're going to have a normal force. That normal force is always going to be perpendicular to the surface. So I'll go ahead and draw that vector. So I don't actually know how long that is compared to the others. It depends on the situation. So it could be that it's smaller than the other two. But I can go ahead and sketch it. So this is a force. It's a type normal. It acts on the magnet, and the source of the force is the surface of the fridge. So the last force we have here is let's go with purple. Doesn't really matter. The last force that we have here is a magnetic force. Now, I'll go ahead and label this. So this is going to be a force. It's type magnetic, Now, what is the feeler of this force? Well, the feeler of every force is the system that you're interested in, the system that you're drawing a force diagram of. So the feeler in all these forces with a magnet, and that's not going to change here, it's still a magnet. So what dealt this magnetic force? Well, the magnet can't deal a magnetic force to itself. There's no other magnet here. So the only choice is a fridge. Now, how does the fridge, which is not a magnet, deal a magnetic force? Well, this magnet induces a what's called a magnetic moment in the fridge. You don't have to really worry about that. But then for that time being, when the magnet is nearby, this fridge itself can act like a magnet. So that's how we get a magnetic force from something that's initially not magnetic. But the important thing is to recognize that the feeler must be the magnet, is the thing we're drawing the force diagram of. So one more thing we could say is that because this is moving with a constant velocity, the sum of all the forces, also known as the net force, must equal 0. Okay. The other thing is we can say is that there's some congruency here. This force must be balanced with this force, and this force must be balanced with this force. We don't know if these sets of forces are bigger or smaller than these sets of forces. I've drawn them bigger here, but there's no way to know that with the given information. And there could be coincidentally that the magnitude of this force is the same as the magnitude of this force, but we should not assume that. That's why I gave them different sets of congruency marks. So that's the first example. I'm going to do one more example now. Here I have a hot air balloon tied to the ground, so it's tethered to the ground. And our system is going to be just the hot air balloon itself. So I'm going to enclose the hot air balloon within a system boundary. Alright. And I'm going to condense the system to a single point. I'm going to sketch a set of parallel and perpendicular axes. I'm going to begin now drawing my force vectors. So I know there must be a gravitational force. And that is again the force type gravitational. It acts on the balloon, and the source is the Earth. The Earth is going to be the source of our gravitational force in all the examples that we do. Of course, you could be on the moon or something like that, which is different, but we're not going to try to trick you. So another force we can think about, well, let's think about this. We don't have anything that's obviously pulling it up, but we do have something that's obviously pulling it down in addition to gravity. We have that rope there, right? So we draw this vector. Now I drew it right on top because I can distinguish that with a different color, but if you don't want to get confused, you could come over here and draw it a little bit to the side. If you want to scooch it over a little bit, that's fine. Make sure it still points straight down. So what is this? Well, that has to be a tensional force, right? So we have force type tension. It acts on the balloon, and the source of this force is the rope. So we have two downward forces here. It's pretty clear that this system's at rest. So if the system's at rest, the velocity is 0. It's a constant velocity, and the sum of our forces must be 0. Well, these definitely don't add up to equal 0, so we're missing something. With a little bit of thought, we know that there must be some force that points upwards, but it's not immediately obvious what that force is. We'll go ahead and say that there must actually be a buoyant force here. air, just like water, is a fluid that can be displaced. And when you displace a fluid, the object displacing that fluid, such as a cork or a rock or in water or a hot air balloon in air, has a buoyant force. You have a buoyant force right now. It's just very small because you don't displace a lot of air. But this massive balloon displaces a whole lot of air with its size. So this is an upward pointing force. It's buoyant. It acts on the balloon. And the source of this force is the fluid. The fluid here is the air. So, unlike our previous example, there's no actual congruent vectors here. It would be impossible. If you have three things, if any of them were the two the same size, then you wouldn't be able to add them up and get zero, right? But what we do know is that this green vector plus this blue vector plus this red vector add up to equal 0. So we could therefore say that blue plus red is together the same length as green. But there's no congruency marks to draw. I think this is the most confusing thing. The idea of a buoyant force on an object in the air. But again, repeat myself, if an object displaces a fluid, like for example, think about the air in here, think about all that air that's been displaced by the size of the balloon itself. So anytime there's an object displacing fluid, or moving that fluid out of the way with its volume, there's going to be a buoyant force. Alright, so hopefully that helped, and we'll add some more example videos as we get into some more complicated situations.